We're going to determine whether this series is absolutely convergent, conditionally convergent, or divergent. So we're going to let a sub n be equal to negative 1 to the nth power over n times the natural log of n. So we're going to do a couple of things. We're going to first check if sigma as n goes from 2 to infinity of the absolute value of a sub n is convergent. So we're going to check if that series in absolute value is convergent. If convergent, then we say it's absolutely convergent. Okay. But if it's not convergent, if divergent, then we need to check if the original problem is convergent or divergent. So if the series in absolute value is divergent, so we're talking about this second scenario here, then we have to go back to the original problem. If the original problem is divergent, then the series is divergent. But if the original series is convergent, so the series in absolute value is divergent, but the original series is convergent, then the series is conditionally convergent. All right? So what I want to do is I want to check to see if sigma as n goes from 2 to infinity of the absolute value of a sub n is convergent. So we're going to start with that. So let's look at sigma as n goes from 2 to infinity of the absolute value of negative 1 to the nth over n times the natural log of n is convergent. So we want to determine if that is convergent or not. So this is going to be equal to sigma as n goes from 2 to infinity of 1 over n times ln of n. And what we want to do is we want to come up with the test. Remember, you have about 10 of them that you can use, pick and choose from, use to establish whether this series is convergent or divergent. I'm going to start, just because I want to talk about it, I'm going to start with the comparison test. If you're going to use the comparison test, you remember you got to get another b sub n or another series b sub n to compare it with. But you have to show that the inequalities will hold true whenever you're comparing something. So let's say that the natural log of n is greater than 1 for n greater than e. So we can say that n times the natural log of n is going to be greater than n times 1, which is n, for n greater than e. If we look at 1 over n times the natural log of n and 1 over n, then we can say that the left-hand side is less than the right-hand side for n values greater than e. So we can say e is approximately 2.71 or an irrational number. So we can say for n values greater than 3. Right? Because n represents a positive integer when we're talking about series. So if we now look at sigma as n goes from 1 to infinity, or in this problem from 2 to infinity, of 1 over n times the natural log of n in the denominator, then that series will be less than n goes from 2 to infinity of 1 over n. We are going to, in a little bit, make the argument that this here is divergent by the harmonic series, or divergent by the p-series test. We are going to make the argument because remember, the harmonic series or the p-series begins at 1 and our series here begins at 2. But let me talk about that in a second. Here we are saying that the larger series is divergent. And remember that if the larger series is divergent, then we cannot make a conclusion about the smaller series. So we can say that the comparison test is inconclusive. So we cannot use the comparison test. So if we can't use a comparison test, we got to use a different test to establish convergence or divergence. But let me go back and make that argument about sigma as n goes from 2 to infinity of 1 over n. That series is nothing other than, let me erase that. So that series is nothing other than 1/2 plus 1/3 plus 1/4 all the way to till you get to 1 over infinity. The harmonic series begins at 1. So what I'm going to do is I'm going to add 1 to that series, and I'm also going to subtract it. So I can say that that is equal to -1 plus 1 plus 1/2 plus 1/3 plus 1/4 all the way till infinity. So you're going to have, and that is infinity in the denominator. So you're going to have -1 plus sigma as n goes from 1 to infinity of 1 over n. We know that this is divergent. That's the harmonic series. That's divergent. So we cannot find the sum. And if you can't find the sum, it doesn't matter what you get when you subtract 1. Okay? That's what I meant by we can make the argument that it's divergent by the harmonic series. So we just established that the comparison test is inconclusive. It can't tell us anything. So because it's not going to be able to help us with anything, what we can do is we can look at the integral test and see where that takes us. So we're going to let f of x be equal to 1 over x times ln of x. Remember, when you're using the integral test, you need to establish those 3 conditions. You need to establish that your function is positive, continuous, and decreasing. So you need to show that the 3 conditions hold true. And then remember, if the 3 conditions are met, and if the integral, I'm going to just write it in general, from 1 to infinity of f of x dx, if that is convergent, so if convergent, then the series is convergent. But if that integral is divergent, then the series is also divergent. Let's make sure that the 3 conditions are met before we continue. So is it positive? Well, we are looking at x times ln of x for x values greater than e. So for x values that are greater than e, we can say greater than or equal to e, we can say that it's definitely positive. Is it continuous? And the answer is yes. We know that the function f of x cannot be 0 in your denominator, but that means x cannot be equal to 0. X is not in the domain that is from e to infinity. So we can say that the function is continuous on that closed interval e to infinity. And is it decreasing? Well, let's look at what happens. Let's look at the first derivative. Let's say f prime of x is equal to, we're going to do the quotient rule. And if we do the quotient rule, we can say that derivative of the numerator is 0 minus the derivative of the denominator. We're applying the product rule there. So we have 1 times ln of x plus x times 1 over x times ln of x to the second power. So here we have negative ln of x plus 1 in parentheses over x times ln of x to the second power. The denominator will always be positive because you have a square. But what can we say? What can we say about the numerator? About the numerator, we can say that as x is going from e to infinity, this is always positive. ln of x, as x goes from e to infinity, is always positive. So you have a positive number plus 1 is positive, but this negative is going to make it 0. Less than 0. And because it's less than 0 from e to infinity, we can say that f of x is decreasing. We're applying the first derivative test that we learned in Calculus 1. So we have a positive function, or we have a function that is positive, continuous, and decreasing. And because the 3 conditions are met, we are going to look at the integral from 2 to infinity of 1 over x times ln of x dx. We have an improper integral, so we're going to have to take the limit. But before we do that, why don't we start by trying to solve this integral using substitution. We're going to let u be equal to ln of x, and du is equal to 1 over x dx. So then our integral is going to become the integral when x is 2, the lower limit is ln of 2. And when x is infinity, as x approaches infinity, ln of infinity is still infinity. And then we're going to have 1 over ln of x, which is u, and 1 over x dx is du. Okay, so one more time. We do have an improper integral. And because we have an improper integral, we have to take the limit. So let's take the limit as t approaches infinity. So we have the limit as t is approaching infinity of the integral that goes from ln of 2 to infinity, but infinity is now t, and then 1 over u du, which is equal to the limit as t is approaching infinity of ln of u, and we evaluate from ln of 2 to t. Again, which is the limit as t is approaching infinity, the natural log of t, minus the natural log of ln of 2. If you look at the limit as t approaches infinity, then that is infinity. And because that is infinity, we can say that the integral from 2 to infinity of 1 over x times ln of x dx is divergent. So sigma as n goes from 2 to infinity of 1 over n times ln of n is divergent by the integral test. Okay. Seems like we've done a lot, so let's go back a little bit. I'll give you a second. We were doing this right here because the comparison test was inconclusive. But we were also doing this here because we wanted to establish if the series of the absolute value of a sub n was convergent. And it was not. We just said that it's divergent by the integral test. So since that series is divergent, and that is the absolute value of a sub n, the series of the absolute value of a sub n is divergent, now we need to go back and check the original problem. So we want to check if this series is going to converge or diverge. I apologize for that. Well, how do you think we can check whether this series here is convergent or divergent? This, because you have a negative 1 to the nth power, we can apply the alternating series. What are the two conditions for the alternating series test? Again, because you have to, because you're going to do the alternating series test, you have to show that the two conditions are met. And the two conditions are b sub n plus 1 less than or equal to b sub n. I'll put a question mark because we need to check. And then we have the limit as n approaches infinity of b sub n equal to 0. We already did the work. We already established that our b sub n is decreasing. So that first condition is met. And remember, we established that it was going to be decreasing when we looked at the function and we did the first derivative test. Okay? So if not, what you can do too is you can say that ln of n plus 1 is greater than or equal to ln of n. It's just going to be greater than for n values greater than 2. We can also say that n plus 1 times ln of n plus 1 is greater than n times ln of n. So we're multiplying by a bigger number on the left-hand side. So 1 over n plus 1, ln of n plus 1 is going to be less than 1 over n times ln of n. And this just showed that b sub n plus 1 is less than b sub n. Again, it's decreasing. So the first condition is met. Now we want to take the limit as n approaches infinity of 1 over n times ln of n. And this is going to be 0 because as your n gets bigger, this is going towards infinity. And 1 over infinity is going towards 0. So the second condition is also met. So since the two conditions are met, we can say that sigma as n goes from 2 to infinity of -1 to the n over n times ln of n is convergent by the alternating series test. So it's convergent by the alternating series test. All right, that's not our final answer. What was our final answer? We were trying to establish if the series is absolutely convergent, conditionally convergent, or divergent. So we can say that since sigma as n goes from 2 to infinity of the absolute value of a sub n was divergent, and sigma as n goes from 2 to infinity of a sub n is convergent, we can say the first one was divergent by the integral test. You don't have to say this part here because you already said it earlier, but I'm just writing the conclusion, okay? And then the series, not in absolute value, is convergent by alternating series test. Then the original problem, the series, we write sigma as n goes from 2 to infinity of -1 to the n over n times ln of n is conditionally convergent. And you are done. I really like these problems because they have all kinds of concepts here. Let me go back to the concepts that we talked about. So concepts in this problem. So what did we talk about? We talked about the comparison test. We talked about the alternating series test. We talked about improper integrals. We talked about taking limits. Sometimes some of the problems will require you to apply L'Hopital's rules. Not in this problem, but we talked about limits. What else did we talk about? We talked about absolute convergence, conditional convergence, and divergence. So there are some problems that talk about many of the concepts here, or many of the concepts within the problems. So as you're looking at section 11.6, and either conditional convergence or absolute convergence or divergence, then some of these problems will require you to do several different tests in one. All right, I hope you think they are fun. I know they're long, but there's so many concepts that makes it fun because it helps you review all kinds of topics. All right, I'm going to stop here. It was a fairly long example.